Chapter 2, Section 3 is on acceleration. And acceleration is when an object's velocity changes from moment to moment. Now, there are two different types of acceleration. There's average acceleration and instantaneous acceleration. Average acceleration is when an object's velocity changes over a period of time, and that's represented by the equation average acceleration equals the change in velocity over the elapsed time, which is v final minus v initial over t final minus t initial. Now, instantaneous acceleration is when an object's velocity changes at a specific point in time, and that's represented by the equation the limit of the change in velocity over the change in time. Now, both of these accelerations have the same unit measurements of meters per second over second, which is meters per second squared, and this can change if your problem gives you kilometers, centimeters, etc. Now, something else that needs to be noted in this section is the acceleration and velocity relationship. Now, if the acceleration and velocity are pointing in the same direction, the object will be speeding up. So, for example, if an object's moving positive 500 meters per second squared and positive 5 meters per second, the object will be moving up. But if the object's acceleration and velocity are moving in different directions, then the object will be slowing down. For example, if it's going positive 5 meters per second squared and negative 10 meters per second, it will be slowing down. Now, a problem from this section is number 15. And part A says, suppose that a NASCAR race car is moving to the right with a constant velocity of positive 82 meters per second. What is the average acceleration of the car? Now, since the car is moving at a constant velocity of positive 82 meters per second, the average acceleration of the car will be 0 meters per second squared. Now, the reason it's 0 meters per second squared is because since it's moving at a constant velocity, it's not speeding up or slowing down, thus the acceleration is not changing. Now, for part B, it says 12 seconds later, the car is halfway around the track and traveling in the opposite direction with the same speed. What is the average acceleration of the car? Now, the velocity of the car is now negative 82 meters per second. And since it's 12 seconds later and they're only halfway through the track, you would take the time and divide it by 2. So you do 12 seconds divided by 2, giving you 6 seconds. Now you would plug this into your equation, which is average acceleration equals the change in velocity over time. So you do negative 82 meters per second divided by 6 seconds, giving you negative 14 meters per second squared. Now, another question you would see is number 17. A motorcycle has a constant acceleration of 2.5 meters per second squared. Both the velocity and acceleration of the motorcycle point in the same direction. How much time is required for the motorcycle to change its speed from 21 to 31 meters per second and 51 to 61 meters per second? Now, the constant acceleration is 2.5 meters per second squared, and this will be the same for both part A and B. The velocity and acceleration are both going in the same direction, which does mean that the object is speeding up, and the time is what we're trying to figure out. So for part A, you would take the final time minus the initial time, which is 31 meters per second minus 21 meters per second. And you would get 10 meters per second for your change in velocity. Now you would plug this into the equation, and you would do 2.5 meters per second squared equals 10 meters per second over time. And then you would multiply time out, giving you time times 2.5 meters per second squared equals 10 meters per second. And then you would get time equals 10 meters per second over 2.5 meters per second squared, giving you time is 4 seconds. And this will be the same for part B, considering that both the change in velocities are 10 meters per second. So 61 minus 51 equals 10 meters per second. Then you would do 2.5 meters per second squared equals 10 meters per second over time. And then you get time equals 10 meters per second over 2.5 meters per second, which time equals 4 seconds. Now, the concepts of this section. Number 7. At one instant in time, a car and a truck are traveling side by side in adjacent lanes of a highway. The car has a greater velocity than the truck has. Does the car necessarily have the greater acceleration? And this is no, because although the car has a greater velocity than the truck has, you do not know the time interval at which both of these cars have been driving. Thus, you don't know how it's affecting the acceleration of the car. For number 8, two cars are moving in the same direction, the positive direction, on a straight road. The acceleration of the car also points in the positive direction. Car 1 has a greater velocity than car 2 has. Which of the following statements is true? So for part A, it's stating the velocity of the car is always greater than the velocity of car 2. Now, this one is not true because although car 1 has a greater acceleration than car 2 has, it does not necessarily mean that it has a greater velocity. It could also mean that it has a smaller amount of time, or car 2 has a greater amount of time. So this one is not true. And that's the same for answer B, because you do not know the time interval. But for answer C, which is actually the correct answer, in the same time interval, the velocity of car 1 changes by a greater amount than the velocity of car 2 does. And this is why it makes it true, because it says in the same time interval. So if car 1 is changing with a greater amount than car 2 does in the same time interval, it will give car 1 a greater acceleration. And why answer D is not true is because it's saying that car 2 is changing with a greater velocity, when in the problem it states that car 1 has a greater acceleration. Now for question 9, an object moving with a constant acceleration slows down if the acceleration points in the direction opposite to the direction of the velocity. But can an object ever come to a permanent halt if its acceleration truly remains constant? And this is no, because if a car is at a constant acceleration, it means it's not slowing down and it's not speeding up. So if it's not slowing down, it can never permanently come to a complete stop. Now for question 10, a runner runs half the remaining distance to the finish line every 10 seconds. She runs in a straight line and does not ever reverse her direction. Does her acceleration have a constant magnitude? And the answer for this is no, because although the runner runs half the remaining distance to the finish line every 10 seconds, we don't know how long it took her to run the first half. So you would not be able to tell if the acceleration has a constant magnitude.